go over some more examples, and more addition to what we talked about. I did a Blackboard announcement on this. The molecule we did on Wednesday has an extra 5 added in.
My bad.
Easy to have it. So here is our structure that we started with. We had 253 and 30 and 3 times 5 for the alkyl groups and 60 for the amine, and we came to the total of 358. I neglected to add in the exocyclic double bond. So if we look at this ring here, there is a double bond that is exocyclic to that ring. This double bond, one of the carbons is attached to the ring, but the other one is outside of the ring. And so that's considered exocyclic, and for that we need to add 5 more. And this takes us to a value of 363 nanometers instead. The question was asked whether we should always choose the homoannular or the heteroannular. There's a couple different ways of answering that. One is that if you choose the homoannular, the fact that this is a diene inside of one ring is accounted for already. If you wanted to, you could choose the heteroannular, but then we have to add an additional correction factor that counts for the exocyclic, the homoannular ring there. So if we were to do that, we would start with 214 as our base value. Write my own. So 214. Then we're going to add 30 for our extended conjugation. And because the extended conjugation would be part of the homoannular ring, we would add 39. Any dienes that you have that are homoannular, you're going to add 39 for. So if you have multiple that are homoannular, you would add 39 for each of them. That's what the worksheet says.
I don't understand the difference between endocyclic and exocyclic when it's either or.
Trying to think if there's another place there mentioned in those rules. Okay. This is considered endocyclic, and this is considered exocyclic. And when you have multiple rings connected to each other, you have to look at both different rings, because this has 2 endocyclic rings, but this one has an endocyclic and an exocyclic. So we count it, even though it's endocyclic to this ring, it's exocyclic to this one. So all the exocyclic add together. This is just one. There's just the one that it's exocyclic to. Anita had a question.
So essentially you're saying you look at them separately in terms of...
Yes. So we look at this ring and we say, oh, there's one exocyclic here. We look at this ring and we say, there's nothing exocyclic to this ring. Was that your question?
Kind of. So in case of 2 connected rings, 2 rings connected by double bond, the single bond can be exocyclic to both?
Yes. So you look at each ring individually and you determine what's exocyclic to it. So we do have the same 15 alkyl here, 60 for the amine, and the 5 for the exocyclic. And that should add up to 36 nanometers as well. So it doesn't matter which one you choose, but you have to take into account the homoannular ring diene system in some way. The first way puts it into the base value, the other way adds it to the set of calculations you're doing. Which I then went to my book and I added homoannular diene plus 39 at the bottom of their table because any homoannular diene needs 39 added. Let's see. Oh, get rid of that. It did not save. I found this chapter that was talking about the UV vis spectra of steroids. So here would be a cholesterol type steroid where it has a 5,7 diene. So if we were to look at this one, we would look at it and we can calculate the lambda max it should be at. We will see a homoannular diene here. So we'll start with that 253 nanometers. There are 1, 2, 3, 4 alkyl groups. So we're going to add 20 for the alkyl groups. And then if we look at the ring structure here, this double bond is exocyclic to a ring. It's exocyclic to our first ring. And then the other double bond is exocyclic to another ring. So both of those would count as exocyclic. And so we would have 2 times 5 for 10 for our exocyclic. Where this is our exocyclic point here and here.
Never mind. Nope, and gone.
I believe that is all that we need to add for that one. No extended conjugation and no polar groups attached. So if we add that all up, we are going to get 283 nanometers for our lambda max. And here's the UV vis spectrum. Which is somewhere in the range of 280 to 285, I would say. Not quite sure exactly on that one. Now you'll note that there are other maximas. These depend on those vibrational and rotational states a little bit, and it also depends on the solvent you take it in. So we might see that and we may not. There's nothing else particular about the structure that would correlate with another lambda max that we would look at. So we don't have any other conjugated systems, and so I believe that this is all from that one system. This is the homoannular diene. They have another alkene. also a cholesterol derivative. Cholesterols have the 3 cyclohexanes and then a cyclopentane attached in the same core structure every time. Because this is now a heteroannular and there's only one exocyclic, we can do this calculation. So we have 214 plus, if we look at alkyls, we have 1, 2, 3. 3 times 5 would be plus 15 for our alkyls. And we only have one exocyclic double bond, and so we would have 5 for the exocyclic. So we'll add 5 more. So this gives us a lambda max of 234, which here is our lambda max for that diene. Yeah.
The other piece of myself, because I
Mhm.
lost count. Like if I was looking at this, I would think that the lambda max was like 200.
Right. Now note that they are extending this to a little bit below, and that gets into some of our other functional groups that we don't normally see. It may be, if we look at our chart here, could be an alcohol into pi star, or it's essentially our only functional group there, so I would maybe see it was an alcohol. It's shifted a little bit from what a standard alcohol, and I'm not quite sure why we don't go into too much detail when we're looking at alcohols, because they're not as consistent as the dienes in terms of shifts. I wanted to do some enone calculations, so we're good on dienes. Okay, let's go to the enone. So simple enones are going to have slightly different rules than the Woodward-Fisher rules that we were using for the dienes. First off, we're going to start with a different functional group as our base. So you're going to have an alkene and a carbonyl that are conjugated together. So if we start this, as our base one, then we'll need to go to calculations for a correlation table. And again, on this one, we are looking at the pi to pi star transition. This is going to be the stronger transition. If we look at carbonyls, they can have a pi to pi star or an n to pi star. Now the pi to pi star is usually outside of our range, but if we add conjugation, it's going to move it within our range. And it has a higher epsilon, so a higher intensity. The n to pi star is a forbidden transition, which means that they're relatively weak, so they won't show up as well. And as we get to enones, they start to dominate the spectra, and you can cover up this n to pi star. So we are specifically looking to do the calculation with a pi to pi star. So we'll start with our table here. We're base value for a 6-membered ring or acyclic parent enone. This is going to be considered acyclic because the alkene is not part of the parent, even though it's part of a six-membered ring here. It's not within the ring. So we're going to call this an acyclic parentenone, even though it's attached to a ring. And so our base value is going to be 215 nanometers. The adjustments that we now have to make are going to be slightly different than the adjustments we make for a diene. The values vary, and it's also important to consider where things are attached to the ring. And if we're talking about carbonyls, this is our alpha position, this is our beta position, and if we had anything attached out here, that would be gamma. So for this, we have alkyl groups. We have one alkyl group, alpha, and for an alpha alkyl group, it adds 10 nanometers. For beta alkyl groups attached to the beta, this is going to be 2 times 12. 24 nanometers for our beta alkyl groups. And we have our alpha alkyl here. You also have adjustments for polar groups, and again, it matters where they're attached, so alpha, beta, gamma. And bottom of the table here, we have an exocyclic double bond and homocyclic diene. So if we had a homocyclic diene, we'd add that same 39. And exocyclic double bond is the same at 5. So we have on this one 2 exocyclic double bonds. This ring has this carbon of the alkene being exocyclic. This ring has this carbon of the alkene being exocyclic. So this is 2 times 5 to add 10 total for the exocyclic.
What about the carbonyl?
We don't add anything for the carbonyl because it has to be exocyclic. Because the carbonyl oxygen can't take any more bonds, it only wants to. You don't correct for that at all. That's kind of part of the base value.
I'm not sure if you're gonna address this, but then off the carbonyl, is there a ring residue there with that double bond? Does that count?
We are talking about a ketone. The enone is a ketone base structure, so no. The aldehyde has a different base value that we would look at. And so you would account for that difference that way. So our total here should be 9, 1, 2, 3, 4, 5, 259.
Is this an acyclic parentenone because the double bond is off of the 6 ring, or is it because of the ketone?
Because of the double bond. A cyclic parent would be the double bond inside the ring. And they also talked about the 5-membered rings, so that would be the same.
And then what is homocyclic diene component? Is that just like if you have a double bond with
It's
anything?
this same structure. Oh, need that. If we had 2 alkenes attached in the conjugated system,
So like if there's 2 alkenes in the what's that? In the top one?
yes. Yes, and we can do another example like that.
If it was in the top one though, wouldn't it be the parent, not a component?
No, we still count the enone as the parent because well, we have correction factors for dienes, but not for, we don't have a correction factor to take the enone and factor it into the alkene.
Wouldn't they both be enones though, because they're both attached to the double bond
No, just the one with the ketone in it.
with the ketone?
Let me draw it in. I'll draw a structure and then we can talk about it.
Okay.
So here, you might be tempted to say, oh, this is a diene, and then we have to calculate from there. But we have no correction factor for a carbonyl. So instead, we want to count our parent as the carbonyl and the one alkene. So it's an enone. So we'll start over here. Now we have a 6-membered ring, parent enone. This is the cyclic version because the alkene is within the ring. And that gives us a base value of 215 nanometers. We've got extended conjugation, so we've got 1, 2 double bonds that are extending conjugation here, here. So 2 times 30 for 60. Then, going down, we have the alkyl ring residues, alpha, beta, delta, no, sorry, gamma first. And that's as high as we need to count, because anything past gamma is the same. And so for our alpha, we have nothing. Beta, we have one substituent there, so we have to add 12 for our beta alkyl group. Then as we go around the ring, gamma doesn't have anything, the next one over, nothing, but this one has, oh, same thing again, but it's attached in a different place. So it counts both as the gamma and, or sorry, both as our beta and the gamma or higher substituent.
Wait, go through this again?
Because it's attached here
I missed the green box.
and here. The green box is the beta,
Okay.
so it's attached beta. It's also attached at the end of our conjugation, which is the gamma or higher.
So you count it twice?
Count it twice, well, in different ways though, because beta is going to add 12, gamma or higher is going to add 18. So now we're going to add 18 for our gamma or higher alkyl. And we want to look at our rings here. So we have no polar groups. We're going to then go to the next part. Exocyclic double bond. To this ring, there's nothing exocyclic, but if we look at this ring, this one's exocyclic. So we're going to add 5 for our exocyclic portion there. And homocyclic diene component. We have 2 alkenes here that are within the same ring, and so they are going to be considered homocyclic diene. We add 39 for that.
Oh, no, different question, sorry.
Okay. So this adds up to 9 Let's do.
I hate these.
We're having a
I
little
don't
side
make-
discussions about the aldehyde in the homework.
Yeah.
Where do we start with that?
Yeah.
Different derivative.
Let's just do the homework.
So here we go. We have a. If you have an carboxylic acid, start at 217, and if you have it's attached in a 7-membered ring, that's going to add more. But then you go back to this table for all the fractions. Wow, that seems very dramatic. So you would start with your base value from here, and then
But
correct it with
is that another
these
table for
values.
aldehydes on the other?
There,
Carboxylic.
for aldehydes,
So the base value is 2.
the base value is 208.
So we should start.
The alkyl and the beta here. So if we go to 208, if it has an alkyl or a beta, it adds 12. If it has an alpha beta or a beta beta, your base value is going to be 230. Or if it's alpha beta beta substituted, it's going to be 242. Those are your base values, basically.
What is beta beta?
It means it has 2 bases.
Really?
No, we start.
The picture.
This is alpha substituted. This is beta substituted. You can have alpha and beta substituted. And then alpha and beta beta substituted. So this would be alpha substituted, beta substituted, alpha beta, and alpha beta beta.
What if it's that one on the right without the top arm?
Now this, it would be beta
It
beta.
would just be beta beta.
Sound like we're starting fraternities here. Beta beta. Alpha beta beta. I don't think that's fun.
Zeta? What? Yeah, now what?
Any other combination? I don't think there's any other combinations I can make.
And that, the fourth one in, that's a single bond, not a double bond.
Yeah,
Okay.
started putting the double bond up here on accident. So with these, then our parent is, it's not substituted at all, so it would be 208. If it's either alpha or beta substituted, 220. If it's alpha and beta substituted, it's 230. If it's beta beta substituted, it's 230. And if it's alpha beta beta substituted, 242. I know.
Then you go back to the other table for
Or
like,
any other
everything
correction
else.
factors.
including like gamma alkyls and that sort of thing.
Yes. So it then says that the empirical rules listed, or 7.8 is the empirical rules, but they follow the same general rules, oops, I'm way off, as the enones, except for where they start, basically. So, and then you don't do any more correction for the alpha and beta substituents, like we did on the enones. So you're not going to add another 12 or another 10 for the alpha and beta. You've already accounted for that here.
Okay, I figured that out on this one.
No good way to ask this question. We have to have all of that memorized.
No, these tables, if I'm going to make you do these calculations, I'll give you what you need.
Unless they're really, really easy ones.
Compare. There we go.
No, I'll give you what you need. Okay, let's start. What shall we draw? Like, oh, Martell, nice try.
That was so
Good enough.
Cool.
Okay, let's
Dear God.
calculate this one, and I have not calculated this one ahead of time, so I'll bring it together.
It's staying up, so I'm gonna let it be.
So which one should we start with? What should our parent value be?
So it would be 220.
So we're debating whether it should be 220 or 230.
No way.
As to whether we count this one as beta substituted.
No, is this in the conjugation?
In general, we don't count it when it's part of the conjugated system. So we're going to start with 220 for a beta substituted alkyl. Remember, we're talking about the alkyl substituted. Yeah.
Where are we seeing that? Is that the bottom?
This is going to be our parent.
Why is it not beta beta?
Because the other part is part of our extended chain. Yeah. So if it's part of the extended chain, we don't count it.
Don't worry about it. Extended chain.
Then we go with, so we've already accounted for, actually I'm going to extend this out and say we've accounted for this alkyl group. So we don't try and count it again. So it's our beta substituted enal. Then we are going to look, we have 2 extended conjugation. We have 1, 2 alkyl groups that are gamma or higher. So we have 2 times 5, no, sorry, I changed here, 18. 36. No polar groups attached, unless you want one. Should we put one in?
Baby
Why
steps.
not?
Baby steps.
We haven't done any yet, though.
Wait, do it on the next one.
Next one.
This can't
You want me to do it?
This
No,
isn't
no,
the last one.
You guys are having so much fun with this, you want it to keep going?
We need more help.
So we have this OCH3 group, which is attached way far away. Do I want to do that?
Wait, what's
No.
first?
I don't want to put it that far away. It's not on our list.
But I just wrote it in pen.
I just
Well, the problem is that it greatly affects it, whether it is alpha, beta, gamma, delta. And I think there would be like, if it was the next one out, it's going to be less than that one.
Why does it jump out?
So it's on gamma?
Because it depends on whether you can actually donate these into resonance to up here. So it is on gamma.
Wait,
Can you show us?
why is it not on alpha?
Alpha, beta, gamma.
Okay.
Freaking weird looking. Trying to
So
draw.
that adds 17 for our gamma OCH3 group. Now we want to look at exocyclic double bonds. So we have 1 exocyclic double bond here, 1 exocyclic double bond here, do times 5 for exocyclic double bonds.
Wait, why? Oh, I see.
We do not have a homocyclic tying component, and there was one more. Oh, the solvent effect, which is variable. Yeah. Ah, 3, 9, 12, 14. 343.
Is there any reason why our calculated value highly differ from the actual value?
These are all theoretical based on model systems. As they get more and more complex, they may differ more significantly. I don't have a, I just made up this molecule. I don't even know if it has a UV value.
You're like, you're right.
Here, I believe they have several examples. They have one example. It's not really that close. So they do value differ. I guess if we look at these enones, we can see they have your experimental for something pretty simple. It's going to match pretty closely. As it gets a little more complex, they get off a little bit
Should
more.
they ever differ by 50?
By 50 sounds a little high, but that is rather complex right now.
Yeah.
Yeah.
A little bit.
It's only 47.
Only 47. Oh, yeah. Okay. No, they do differ as they get more and more complex, and the extended conjugation affects it, and so, yeah.
What are the red squares? What are the alpha plus, or the
The
gamma,
gamma
plus?
plus
Does that mean just like anything over?
gamma.
And it could
So-
go way more over?
Right, so it's gamma or higher groups that are attached to gamma, carbon, or higher in your calculations. How are we feeling?
Lots of outside
Pretty
practice.
exciting doing these calculations.
No, I think there's so many rules that I just got lost.
Yes, there are a lot of rules. Hopefully these are the ones you really need to know, because the enones and the dienes and then carboxylic acids and other carbonyls are the only ones you really do calculations for. Everything else we do not.
Okay, so I'm confused. Is there a difference between like enones and then having like an aldehyde or whether or not it's like in
If it's acyclic or exocyclic.
yeah, I think I realized what it is.
Okay. I don't see anything anywhere in there.
If you have a double bond, or a double bond, this is going back to what Luke said earlier, if you have a double bond in between the two rings, that's two.
Like that one?
Well, no, it's like that on the side, but you have another ring attached. So that's the one that's in those.
Like this one?
Yeah, but if it was the double bond.
If there was another ring here?
Well, then the wall's right down the middle between the two. Yeah, that'd be two.
Huh.
Yeah. Well,
I don't think so. I don't think it's exocyclic to anything. Because it's endocyclic in this ring and then it's endocyclic in this ring.
Sitting down now.
This is what you're asking? Not endocyclic, not exocyclic, anything. So if we look at this ring, it's endocyclic. If we look at this ring, it's endocyclic. Okay. So no correction for that one.
That also has.
Struggle with it. No.
Yeah,
The triangle.
would you mind moving back like 2 pages?
Do you want this guy
No.
or?
One more. And then on the right hand page, it says for the, your ring residues, it has, on the right hand example, it says 5 times 5, and I couldn't find 5.
So here we have one there, one there, 3, 4. Tricky one goes back to where we started here.
What?
That one,
We already counted that one. Oh, but we counted
but it's
twice.
attached in a different place. It's attached to
Okay.
Oh, this is kind of.
places, to the alkenes, 2 different alkenes. Yeah.
Thank you.
Is that the same
There's no
level
better
of
choice.
Just getting comfortable.
It's just like running hundreds.
I wanna go.
I'll let you work out some of the other examples, say, in the end of the chapter, or things like that. If you still have questions, let me know. What are we looking at in UV bits?
Electronic
Essentially, you're going to look to see whether there are peaks. This is a summary of the last page of the chapter where it says the different chromophores and what they would represent, or what you would look for. And then also in your UV biz, you would look for the peaks and what their absorbance is. That's essentially what you're going to report. So if you have just one band and it's not very high lambda max and it's not very intense, you would think alcohol, ether, amines, thiols, and nitriles. If you have one band and it's somewhere between 250 and 360, and it's very low intensity, a simple chromophore like a carbonyl, diazo, nitroester, carboxylic acid, or an amide, so things that have double bonds as part of their functional group. But these are the low intensity, and that's the chromophore by themselves. If you have 2 bands that are greater than 200 and they are medium intensity, probably thinking that it's an aromatic ring. And if you have one band greater than 220 and it's really strong, we're going to start thinking it's a conjugated pi system of some sort. So carbonyls, dienes, things like that. If you have 2 bands, one that's greater than 300 and not very intense, ketone, ester, or carboxylic acid, and it has a second band that is less than 250 that is intense. Yeah, same thing. So you need one band greater than 300, not very intense, and one that's less than 250, and it is intense, then you're going to think of those functional groups. If it's highly colored, greater than 380, it's going to be a highly conjugated system, so you have lots of double bonds. And the one we've been looking at in lab, you know that there's 4 or 5 phenyl rings hanging off of that, and so it's a highly conjugated system. Most of these assumptions you would want to verify with some other method of spectroscopy. So using a IR to confirm that yes, that is an alcohol, or a NMR, or something that confirms this. I would not just look at the UV vis and say, well, have to have a ketone, and that's the only thing I'm going to think about from here on out when I'm identifying this. No. Be careful with that. Let's talk a little bit about color. sample, the light that goes through the sample, some of it may be absorbed if it's a colorful sample. And that light that gets absorbed, you're not going to see quite as intensely. So when we're observing the color, we're observing things that pass through it rather than what's being absorbed. So when I look, if you were to look at this sample and it's absorbing this yellow-green, you're going to then kind of combine everything together and think it's kind of a pinkish purple color. You see what's not being absorbed. So if we compare that with the UV vis, you would be observing what's being absorbed, because that's what the UV vis is calculating. And in the UV vis, we would measure a strong absorbance of this green color. And that's when we talk about the complementary colors. So you are seeing what complements what is being absorbed. So if red is being absorbed, you're going to see more of the blue-green color because that's what's passing through, and we observe the blue-green color if it's red is absorbed. Conversely, if the blue-green area is absorbed, we're going to see red as the complementary color. That's what we observe on the other end. What do you see if, let me make sure I get this right. If everything is absorbed,
I think those colors don't go together.
Here.
so we've got white or black as our option.
White is everything and black is nothing.
It absorbs all the light.
I used to know that.
I don't know. That's what I was thinking. It absorbs all the light. It's just like that's what comes to mind. Wikipedia.
I believe it's black. What's being absorbed?
It just reminds me of like a black hole. It absorbs all the light. Does it really matter? Nice to see the chance.
Yes! Absence of any color. So when I look at Haley's shirt, we're not seeing anything being reflected back, and so it appears black to us. White, on the other hand, is everything is being reflected back to us.
Prism.
And so we just see a white color.
There we go. Magic school bus, come on.
And Puritans on black.
What?
They had Protestants and Puritans as one of the subheadings.
Probably like why they wear black clothes.
How do you, it's just this weird that like that made that major a heading on Wikipedia.
Puritans. She was commenting on how on Wikipedia, like Puritans was one of the subheadings under the color black. So we were like, of course they
I
would.
completely skipped over. You guys want to learn that from the book?
What?
Aromatics. There's not, we can't do calculations with aromatics because they're not as consistent as the other ones. There's certain effects, so if you have an electron withdrawing group, it's going to affect it differently than if you have an electron donating group. So let's say we have this. X, if it's an electron withdrawing group, is going to shift your second band. No, sorry, it doesn't shift your second band very much, but the electron withdrawing group, or the electron donating group is going to shift our secondary band. Wait, I just said that. Remember in the aromatics, we're seeing a primary and a secondary and a tertiary. Go all the way back here, or sorry, two primaries and a secondary, but the two that we see, the primary and the secondary, are rather weak. Electron donating group, it's going to shift the secondary band.
Which way?
Yeah.
Like, what kind of shift? Ah, there it goes.
Let's see if we can compare some here.
Donating.
And some numbers here.
That is a one.
It is the electron donating group, OCH3. You're going to look at a plus 13.5 approximately. The electron, that's the one, this one I'm looking at. Yeah, I know they're confusing.
Plus 135 or 13.5?
13.
I was like, that's a lot.
Wow.
But that's just the one
All the way down.
example.
We're really toxic today.
It's Friday.
Not here.
Sample spectra. So if you have that methoxy there, we're shifting that one peak up a bit from 200 compared to standard benzene here. And toluene shifts it slightly. If you add conjugation in, we're going to be shifting more. It's not quite as additive. So for some, so the nitro here actually shifts that peak down a little bit. We don't see it quite as much, but we see more in this region. They're just rather complex because they have so many bands. But you're seeing kind of a larger band and then kind of this broad, sometimes jagged, you tend to think aromatics. Yes. So if you remember in OChem lab, you did all those diazo dyes for the tie-dye lab. And that was making the diazo, and then you've got two phenyl rings where your extended conjugation through them, and depending on what substituent you put on those phenyl rings, you got different colors. Because some are electron donating and some are electron withdrawing. We tried to find the rules to do calculations on those.